Good morning. It's my honor to be invited as an invited speaker for the ICMSDS, right, 2020. Thanks for Professor Lesmana for the introduction. Okay. This just give the brief abstract of my talk today. Okay. It's refer to the paper that was published, I think, last year, okay, with my former doctoral student, Dr. Pisak Vitya Papakon. He's now currently serves as a lecturer down there in the north part of Thailand University. Okay, so but I'm not gonna read this article for all of you. Okay, I have some PowerPoint to, but it's just a basic to introduction about me and my co-worker. Okay, and okay, so we go ahead and get started with the PowerPoint presentation. Okay, actually I will go to the point that since this is a mathematics and statistics conference, we show you more about mathematical notation so that you all familiar with what I did. Okay, let's just say that we're trying to solve this problem first. It's a classic production planning under time varying demand, except that the time random demand was represented as a discrete random variable for each period. Okay, you have n, small n as a number period. And exabyte is a lot size for each period. Okay. And due to the uncertainty of demand, okay, K, the index K represents the scenario that all combination of uncertainty can happen, which can be really large. Okay. You all see the slide, right? Okay. You all see the slide online? I think. Due to the combination of uncertainty, the decision of exabyte here, okay, need to take a risk that sometimes they can fulfill the demand, sometimes they cannot fulfill the demand, and sometimes they fulfill with the inventory, and sometimes they need to have some back order. So the I minus I sub k refer to as the back order, the negative inventory for period I at scenario K. And for I plus is a regular inventory, the positive inventory. So this is actually the very well-known model, okay? But it just when you add the uncertainty for the demand, okay? So and with the combination of the uncertainty, for example, for n period, for each period you have 3 possible uncertain demand. So the scale, the possible all possible value of K can be up from 1 to 3 to the n. Okay. For example, if you plan for 12 weeks or 12 period, you end up having 3 to the 12. Okay, that can lead this problem to let's just say not only large, a really large scale model. At one point, okay, you're gonna reach the limit of your computation hardware. That's very hard to say now today because of the advancement of the hardware with the parallel processing and the cloud computing and all that. But let's just say that we add more combination of the uncertainty. Sometimes the model reach the limit of using the direct software. Okay, so we trying to apply what we call the classic vendor decomposition. Decomposition is like the idea had been initiated for a very long time that we trying to decompose the large problem to a smaller problem, and we expect that the smaller problem can be solved efficiently. Okay. So this is how we decompose the problem. We decompose the x sub-I to one problem. Let's just say it's a master problem. And the sub-problem becomes just only I plus and I minus. And we would like to show you that the smaller problem can be easily solved But at first it's not doesn't look trivial. Okay, let's just look at the how the procedure starts. Okay. First, we try to write the dual model here, and with this formulation, I can initiate any x sub I value, and with I plus and I minus variable, we can always balance this equation. But that's not a very good idea to just randomly just pick up every x sub I value. Okay, you might use as a regular let's just say rule of thumb that you're using day by day in practical. Okay. So x star here, okay, is become the initial variable that you set. Once you initiate x sub I, okay, the remaining variable that you need to solve is only I. It's only I plus and I minus. Okay. So in the second stage, once you initiate the x sub I, you move x sub I to the right hand side because it's already a constant value. Okay. Subtracted with the original right hand side, d sub I k. And you rewrite this problem as a dual model. Okay. So the right hand side becomes the objective for the coefficient for the in the objective function of the dual model. And for each constraint, you have y sub I k as a dual variable. And for this constraint on the left-hand side, you can transpose this and rewrite, refer to the variable y sub I k using this formula. And the coefficient for the I minus and I plus for the original primal objective value or objective function can be the right-hand side here. Except for when I equal to n, you don't have n plus 1 anymore. So when I equal to n, you can see that in the last one, you have only one constraint here. You don't have y sub n plus 1k. Okay, so this is a dual form once you already decompose the problem. Okay, so the first stage is you initiate the x value, and then you get the remaining variable I plus and I minus, and you move it, write a dual model. Okay. Once you already write a dual model, if you solve this problem, which is not trivial, when you look at this formula, it's not trivial. Okay. And when you solve it and you did get what we call the optimum solution, we add one more index of j as a number of iteration, because this process you need to iterate it before you can reach what you call the strong duality, when primal and dual meet the objective meet each other. Okay, so j is the iteration number. Okay, and you can move this to the original primal problem. Okay, so this is actually the objective for the dual for the dual problem. Because if you remember that x sub I is already initiated, actually it's a constant here in the dual model. So this becomes the objective for the dual problem. But with the weak duality theory, you know that the objective function for the primal problem has to be, they cannot exceed the objective value for the primal problem. And this is already well known, just an application from the Bender decomposition problem, that it becomes the sub problem to find a new x. You remember that y is solving the dual problem. And then once you get the y value, you want to get the new x value. You're using this as a weak duality theory to set up this problem. And sometimes they call optimality cut model. And certainly, you know, Bender decomposition, there's some way that you might face some infeasibility. So there are two types of cut, the optimality cut and infeasibility cut. But in this case, based upon the model, we don't have to worry about infeasibility cut. So you need to solve this problem to get the new x sub I value. Okay, and repeat the process again. Okay, once you know the x, you're going back to the primal model to replace the x from the previous iteration and recompute the y again with j equal j plus 1. Okay, so let's go back here. Once you get the new y, you add this as additional constraint, and you stop when t is convergent. Okay, and when t and c here, okay, the let's just say the objective for the dual problem is equal to the primer that reach the strong duality theorem. That's already well known if you know Bender decomposition. So it's just an application to solve this problem. But the key problem is that how we can solve this problem efficiently. Okay. It doesn't look obvious here, but certainly have some recurrent relation yi sub k minus yi plus 1 sub k, except here. Okay. So we need to develop some, actually Apisak, my student, okay, is a guy who tracked down and be able to develop this algorithm effectively. Okay. So we're going to do that, how we can solve this problem, make this problem to be solved as a trivial solution. Okay. First of all, okay, we need to identify, this is the original model. Okay, we identify, reformulate the problem by identifying the new variable we call u sub I k, and this one also, u sub I k and plus this relationship. Okay, y sub I k. The relationship between u sub I k and y sub I k and y sub I plus 1k, and replace it to the original model. Okay, so you can see that this is a two constraint. You replace y sub I k with y sub I plus 1 plus u sub I k, and this one minus u sub I k. So this one cancel each other, so you get only u sub I k as a lower limit and upper limit of g sub I k h sub I k, which is the coefficient for the objective function. And for the objective function, this is very interesting. Okay. Once you replace u sub I k, okay, with here, this one just expansion for all I. Okay, and then you start to replace this for each y sub I k. Okay, for this one u sub I k, this one u sub 2k, u sub 3k. And again, you know that y sub 2k can be used this formula to replace also, okay, for each of these. So the term can be keep expanding until you reach the limit of I, which is n. The last one is u sub nk. You have no more expansion for it. So with this one, u sub 2k, you can keep expanding until you reach y sub nk. U sub 3k also, you can keep expanding until you reach y sub nk. So you end up giving, reformulate the problem by reformulate the y to become with the new variable u, except y sub nk here, because y sub nk is only individual and independent constraint. Okay, so in the next process, you trying to regroup the term. This is a basic algebra, you know, for all you mathematicians. We see that u sub 1k, okay, we become only the objective function here, but u sub 2k, you have these two terms. U sub 3k, you have these two terms. Okay, these two terms for u sub 2k, the cumulative term. And u sub 3k up to n minus 1, you have cumulative for d sub I k minus x sub I up to I equal n minus 1. So this make it to rewrite, okay, you can see that we reformulate this problem with from y sub I k, I equal 1 to n minus 1 to u sub I k, and end up having only the last variable that still remain, which is y sub n k. And if you look back at the formula here, okay, we reformulate this problem to this, and u sub I k is a bounded variable in y sub nk with this relationship. So you can see that this problem becomes trivial to solve. You don't need any software to solve this problem because you just look at the coefficient that multiply to u sub I k. If it's positive, since the objective is to maximize this function, if u sub I k, this coefficient that multiplied to u sub I k is positive, you just pick the upper limit. And if it's negative, you pick the lower limit. You're going to end up having the maximum value of W. So this is what we call special purpose algorithm we add to the model. Okay, and you know that with this transformation, you don't need any software. You can write your own code to solve this problem. It becomes a trivial solution. Okay, so I just code this, okay, using Matlab, and also with Apisa also we helping each other to code some part together. And luckily, Kurobi is available in Matlab at that time. Kurobi, as you know, that is a extension of the CPLEX for the Excel, okay, for the Excel format. But it become available with the as a object in the Matlab programming. Okay. So we use Matlab environment to solve this problem. As you see, this is the numerical results. That actually the problem consists of 6 periods, okay, and 6 period problem, okay, which n is equal to 6. This is the number of scenario, which is k, the running number of k from 1 to 100, 500. And you randomly generate these by k based on any uniform distribution assumption. Okay, so the size of problem start increasing, but it's actually still don't have any integer constraint. But you can see that Kurobi at one point start to increase. Actually, you can test this program up to a multi-million variable because as you know that nowadays we can solve linear programming a very large scale up to a multi-million variable using the current state-of-the-art hardware. Okay, but the vendor approach, okay, with the reduction of the special purpose algorithm, adding to solve the sub-problem, I think that we achieve that you can look at the graphical solution here, that the Kurobi have start increasing when they start reaching the uncomfort zone because due to memory requirement and within the hardware. But for the vendor decomposition, since we already reduced the model to only X, you know that for some problem we solve only X, we erase all the I. Because all the I, we solve the dual model to get the dual variable Y sub by K. So we don't need any much memory to solve this problem. So that's the very first results, okay, for us, okay. I'm going to switch back to the original paper here, okay. That's a basic idea. Actually, we wrote that paper in Thai language for a Thai journal. But for the publication here, okay, we add what we call, I'm going to try to be brief here. I think that it's open access, okay, this journal. So you can get into the journal website and download it for free. Okay, so we add what we call the fixed charge problem to the original Wagner-Witten's classical dynamic loss sizing under time varying demand. You know that we add with this variable PT. But actually, this one just to make a sub problem a little bit more difficult because you need mixed integer programming routine to solve it. But again, with this X variable, we add to the optimality cut model. But certainly, the sub problem of I plus I minus still hold the same concept that I already showed. Okay, so this one is already show the concept, the previously that I just mentioned to you. So the result is not, this is just the same as I showed you in the PowerPoint, okay. And so this one, he just comparing with the mixed integer linear programming, which is a Kurobi in this case. And we now know that when you increase scenario, but you can see that for not a very large problem, this one is only 5 period problem here, okay. And you can see that at one point, okay, BCS is a vendor decomposition, okay, that with special purpose algorithm, that all the problem there, let's see for the graphic here, okay, 5 period, 15 period, 10 period, and 20 period. Okay. This one has more experimental results because of the reviewer request to improve the paper at that time. Okay. So you can see that the processing time of our method, okay, but it's not proven in terms of algorithmic theory yet. Okay, it looks like a linear curve, okay, here, based upon the experimental results. Why this one is a case of MILP that show not to become linear. Okay, so actually the difference between the previous presentation, this paper, and this paper we add some of the fixed charge constraint, okay, to the original time dynamic loss sizing. Okay. Do I have a few minutes left? I think I'm going to show you what we are continue working on a little bit about what we are doing now. Okay, we are expanding this concept to solve this type of problem, which is okay, thank you. We expand this problem to solve add with the cutting stock problem with discrete time varying uncertain demand. And you know that the cutting stock problem have some transformation from the original standard size to you cut the width size to a smaller width size. And without any uncertain demand, it's already a large scale problem. We call the initial programming problem with too many variables, because the number of variables rely on the all possible cutting pattern. Okay, let's just say, okay, I don't have much time. The same concept can be applied here. But to work it effectively, you need to add this work with the column generation procedure, because the original model has so many variables instead. So this work is a combination of the previous work with column generation to work on. And I think that we just go to the what we call the, let's just say that we already have some initial experimentation results here, okay, with period, number of period if we want to do. You have to know that the cutting stock problem is a lot more difficult than the direct production planning problem. And it took a much longer time to solve because of the initial variable. But at this stage, okay, I'm going to conclude overall that the finding that we found so far is that certainly when you add this vendor decomposition with special purpose algorithm, they're going to work well with large scale problem, which means that when you have a large number of scenarios. At one point, the direct column generation cannot work. But this problem is more difficult than the previous problem because of the initial restriction. Okay. We have worked on some heuristic for the heuristic routing algorithm when the solution reach the optimum solution under the initial constraint relaxation. Okay. And our paper have already been accepted for the International Journal of Mathematics of Operation Research, but that was scheduled to publish maybe next year. Okay, so and I cannot share it with you right now. But if you are interested for this paper, you can give me a call, contact with the organizer about my email address and anything. I'll be willing to. Right now, I have the draft that haven't assigned the page number yet. If you are interested to read it, I'll be willing to send it for each of you directly. But I cannot do it publicly, because this journal is not the open access. Okay, I think I used. I'm not sure I used over time or not, Dr. Lesmana. So I'm going to
have another 1 minute, Prof.
Okay, I'm going to stop my presentation and would like to hear some question or comments or some recommendation from anybody who attend this session. Thank you very much.